So question 5 here. They say differentiate between AC, alternating current, and direct current, which is DC. So direct current is a current that travels only in one direction, right? So you could say DC, which is direct current. I just put in it shorthand, is a current that travels in one direction, right? And has a fixed magnitude and has a fixed magnitude, right? Whereas in an alternating current, which is AC, the direction of the current, right? The current reverses rapidly. So reverses rapidly many times, right? Many times each second. And the magnitude varies. To summarize this, I will just put it up here. Um, so DC, the voltage is constant. So the voltage is constant, right? Therefore, the current direction is constant, right? Remember, V is equal to I R, right? And AC voltage changes. So voltage changes from positive to negative or negative to positive, basically. Therefore, the direction of the current has changed. Right, so I will give you a little graph here because you're gonna need to know how to draw the graph and stuff like that. Right, I'm gonna just draw a little sketch of the graph. So you have voltage versus time. So we put time here, right? You could put voltage over here. You don't necessarily put the unit for this sketch here, because but you know voltage will be measured in volts, time will be measured in seconds. So for the direct current, which is the DC, would have a flat line like that, right? This is DC, and for the alternating current, you're gonna have a graph like this, right? Something like that, basically. So this is the Jody electrical symbol of a transformer. So you can get it straight from the textbook. So it will look something like this. So you have your wire coils here, like that. And then same thing on the next side. Right. And then you have the lines in the middle here. One, two, 3. So this would be a transformer. Transformer, right? Symbol. Right, so they say to state two advantages of using that AC, alternating current, instead of direct current for transmitting electrical energy. Right, so one, a transformer can be used to step up or step down the voltage of the electricity. So it does reduce energy losses due to the resistance in the transmission lines. Now, in contrast, DC transmission requires higher voltages to achieve similar transmission when compared to AC, so resulting in lighter energy losses. Basically, for long distances, especially, AC will have less energy loss. Right? So, um, for just to summarize it, for long distances, right? Um, Alternating current AC will have less energy lost when compared to the DC. Another one, DC systems typically require more complex, expensive equipment for voltage regulation, making AC more practical, right? Because it is less expensive, right, for widespread electrical distribution. So AC um, is less complex and cheaper, right, to set up basically. Um, Complete the statement below. Transformers work on the principle of mutual induction, right? Mutual induction. Now, what is mutual induction? So, mutual induction occurs when you have a change in magnetic field in one of the coil. So, change in magnetic field in one of the coil induces a voltage in the nearby coil, right? So, as in the diagram here, right? Changing in magnetic field, right? And one of this coil here will induce a voltage in the nearby coil, right? Basically, the coil is like the wire there. So part C here now, let's say a mobile phone charger contains a step down. This is very important, a step down transformer which converts the input of 220 volts to a working output voltage of 5 volts. If the output current that flows in the mobile phone is 120 milliamp, calculate the input current from the AC supply. Right? So the set is a step down, right? So just for general knowledge, I will draw a little diagram here for the transformer in case they ever ask you to draw one. Right? So it will look like a little rectangle there with a small rectangle in the middle, right? And then you have your wires, your coil of wires. Right? So something like that. Right? The EC here supposed to be okay. We do it like that. Right? You can have a light bulb there. Right? And you have your wires here up and around the coil as well. So you have less coils on the right hand side here. And this is laminated to reduce eddy currents. So laminated iron core, right? So you have primary core and you have secondary, right? So this could be like your primary here, primary, And this could be like your secondary. Right? So I will go much in depth in this right now. So the formula we need to use, we can use Vs all over Vp is equal to Ns all over Np, and that is equal to Ip all over Is. But we don't have the number of turns and things, so we could just omit the Ns over Np. What we gonna end up with is the Vs all over the Vp is equal to the Ip all over the Is. So they wanted to know the input current. The input current will really be the current in the primary coil. So we cross multiply and we solve it for IP. So IP by VP would be equal to VS by IS. So IP primary current is equal to the secondary voltage multiplied by the secondary current all over the primary voltage. So when you make your substitution here, you're gonna have the 5 volts, right? Because that is the output. So this is Vs. You have your input, which is Vp. In output current that flows, this will be Is. But you have to convert this to amperes. So 120 multiplied by 10 to the minus 3 amperes. Right? So you say 120 times 10 to the minus 3. And you divide this here now by Vp, which is the 220. So you get Is to be 2.73 milliampere, or Is to be equal to 0.00273 ampere, right? Yeah, so that's basically the answer there for that. They said to determine the power supplied by the secondary turns, state your answer in SI units, right? So we could use power is equal to current multiplied by voltage. The one is secondary, so we could just say the power in the secondary will be equal to the current in the secondary multiplied by the voltage in the secondary. Make the substitution there, you gonna get well, the current is 120 multiplied by 10 to the power of negative 3, right? Multiplied by the voltage, which would be 5. So when you work out this, you'll get the power in the secondary to be 0.6 watts. Did you get this answer? Let's see. So that's that. The last part here now, they say if there was 10% loss of power within the transformer, calculate the actual power delivered to the secondary circuit. So you lose 10%. So initially you have 100%. 100% is equal to what? 100% is equal to 0.6 watts. But if you lost 10%, right? It's really 100 minus 10, which will really say, you have 90%, right? You're utilizing 90%. So how to solve for 90% here? So now 1%, if you divide both sides by 100, 100 divided by 100 is 1%. 0.6 divided by 100. And then you multiply now by 90. So 90% is equal to 0.6 all over 100 multiplied by 90. So what you would end up with here is 0.54 watts. Now this is one way of working it out. And next way you can say, you know what? If 100% is 0.61, what is 90% of that? Just 90 all over 100 That is 90% times the 0.6. And that will give you the same answer, basically 0.5 watts. Right? So that is the actual power. Actual power 0.5 watt. 0.54 watt, I should say. Right? Two decimal, please. You got these answers, right? Well, this answer, right?